Continuing with our discussion of polynomials, and after having had a good discussion on complex numbers, let's look at an nth degree polynomial, and I write it as p sub n of x, meaning it's a polynomial of nth degree. And the general form of such a polynomial is as shown here: a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus, and so on, all the way down, a sub 1 times x plus a0, which is the constant term. Now, a sub n's are called the coefficients, and we're going to assume that the coefficients are real valued. The n is the order of the polynomial, so this would be an nth degree polynomial. Now, it turns out to be true that polynomials are very, very important in all kinds of science and engineering applications. And in particular, we're interested in the roots of the polynomials. However, sometimes a polynomial can have no real roots. Indeed, on the previous video, we were looking at a polynomial that was x squared plus 2x plus 5, and found that it had no real roots, but it had complex roots. Here, for example, is a plot of that polynomial, x squared plus 2x plus 5. We plot that polynomial, and the root of the polynomial is where the value of y is equal to 0. This polynomial never has a value of y equals 0. All values of y are greater than 0. And it turns out that the values of x that make y equal to 0 are complex valued and not real valued. And since we're only plotting real values along the x-axis, we don't see what those roots are. So let's discuss some of the properties of these roots, and then I'll show you an interesting plot of the characteristics of a polynomial that has complex roots. Assume the coefficients are real. Remember, this is an important assumption here. It basically, we often, I would say usually, in fact, work with polynomials whose coefficients are real. So all the a sub n's are real numbers. And a sub n is a real number, a sub n minus 1 is a real number, a sub n minus 2 is a real number, and a sub 0. They're all real numbers, okay? All real. All real. Now, what I'm going to do, because the roots are in fact often complex valued, instead of writing my polynomial just as a function of x, I'm going to write it as I've done right down here. I'm going to write it as a function of z. Now remember, in the discussion of complex variables, I use z to represent a complex number. Z is equal to x plus iy as a real part and an imaginary part. The reason why I'm doing this is because often the roots of the polynomial are complex valued, so we're interested in the values and the properties of the polynomial as a function of the complex valued variable z. So I'm going to replace all my x's up here by z's. So I have z to the n, z to the n minus 1, and so on. Now, a polynomial can always be factored as shown here. Z minus z1, where z is some complex number, times z minus z2. z2 is another complex number, all the way down to z minus z sub n. Okay, so an nth degree polynomial always has n factors, okay? N factors, always. Now, sometimes it has the same factor that's repeated a number of times. So, for example, z1 could equal z2, and so on. But it has n factors that can be written just like this. So with that, now this means that the roots z1 up to z sub n, if the coefficients are real and we factor the polynomial, these numbers, these z sub n numbers, are either going to be real numbers, real valued, and not complex valued, or if they're complex valued, they always occur in conjugate pairs. In other words, if z1 equals x1 plus i1, if this is one root with these two, and this is a number like 1 plus iy, or 1 plus 2i, then the complex conjugate of this number is also going to be a root. So when we have real coefficients, the roots of the polynomial are either real or they occur in complex conjugate pairs. Let's illustrate that with this polynomial right here. Okay, I plotted the polynomial. I z equal to 0.1, and I have x plus iy cubed plus 9. Okay, so this is my polynomial. It's z cubed plus 9. Now I put absolute values around it because I'm going to plot the magnitude of that. Okay, remember z is a complex number. So in order to see what the magnitude is and see if it's equal to 0, I'm looking to see if the magnitude of the complex polynomial is equal to 0. So I'm plotting 0.1, and this is just a scale to make it look good, is equal to z cubed, that's x plus iy cubed, plus 9. So if I plot that polynomial as a complex number, this is what it looks like. Okay, we have this right here is the real axis, and this right here is so this is the x-axis, this is the y-axis. Okay, so these are complex numbers represented, x plus iy, so this is my complex plane, and this is the function z equal to x plus iy cubed plus 9. Now let's look at the roots. The roots are where this function drops to 0. Drops to 0 in 3 places. Now I said that a third order polynomial will have 3 roots. This has 3 roots. Now we have one real root, that's this root right here. This is the real root, and it's on the real axis. This is the real axis. Then it has 2 complex roots, here and here. And those roots do not fall on the real axis. See, they fall on either side of the real axis. And they are complex conjugate pairs because one is at plus value for y and the other is at a negative value for y. So this is a complex conjugate pair of roots, and then over here is a real root right down there. So that is an example of how the roots of a polynomial are either real or they fall in complex conjugate pairs. So until next time.